we are talking about ellipses. And I said this a few lectures ago, right? These are conic sections. We take a cone. Yesterday we talked about if you cut this thing exactly level, you would have a circle. The intersection here would be a circle. If it's not level, if you cut up here at an angle like that, then the thing that you end up with, if you look at it dead on like that, would be an ellipse or an oval. Okay, real quick, ellipses, they have some interesting properties. One cool thing is every ellipse has two foci. Foci is the plural of focus. It has two foci. That's one focus right there, one focus right there. And we could define actually this thing as the object you get where the distance from one focus, we'll call that distance 1, and the distance to the other focus, we'll call that distance 2, where the sum of those, the distance 1 plus distance 2, is constant. This is not going to come into play with anything we do with this analytically. This is just one way of defining it. One way you could create one of these is if I took a nail, I think I said this before, if I took a nail and drove it into the board right here, and I took a nail, drove it into the board right here, and I took a piece of string and wrapped it around here and left it loose so that I could pull it tight like that. And I take my, my pen and pull it tight and then keep it pulled tight and went around like that, then I would end up with an ellipse. And you can kind of see why that would be the case, because the distance from here to here would be, well, constant everywhere I go. No matter how far I pull, that total distance of that leg and that leg would be constant. So that's how you could, that looks terrible. Wow. Okay, anyway, look at that thing. Okay, so that's one thing. Now here's, that's kind of, you know, how you can define an ellipse. What's actually pretty cool about this though is what that means is that from any direction you go from here, I don't care what direction you go, if you go up in this direction and hit the ellipse, then the angle of refraction, right, the angle that this would reflect off of, you imagine you shot a pool ball or something like that. If this were like they actually have elliptical pool tables, which is pretty cool, that any angle you go from here out, it reflects exactly towards the other one. And so what they have, these are actual things that exist in the real world. They have something called whispering rooms, where one person stands here and here's their ear, and then they talk. Another person stands here at the other focus and they talk. And when as the sound waves go out, they refract and go exactly to here. All of the sound waves, no matter which way they go back here, it refracts and gets reflected exactly to that person's ear. Even the ones that escape back here, they hit right here and get reflected exactly to the person's ear. So two people can be standing in a room very far away from each other with a hemiellipsoid is what that's called, like where the top of the dome or whatever that they're standing in is an ellipse, and you could whisper and hear somebody from way across the room. It's pretty cool stuff. And actually, I think somewhere, I'm not sure where in Washington, D.C., they built a room like this where they put a big table and they would have people sitting to meet at the table, and they'd have they would invite people from wherever, you know, some, we'll say enemies of the state or whatever, or whoever that they're, you know, they're having meetings with, and they would have that party sitting over here at this end of the table. And then they have a really long table over there, and the room itself was an ellipse, and the two foci were here and here of the ellipse. And the people on the other end of the table didn't know that even when they were whispering to each other, the people over here could hear it. It's devious. But anyway, so that's one final thing about ellipses is for a long time, people thought that the planets moved in circular orbits. Sometimes they thought these circles went around the Earth. Sometimes they thought that the sun was at the center of the solar system, but they thought, well, of course, it's the heavens, and so it has to be perfect. And so the orbits or the trajectories of these planets must be perfect circles. It turns out that they're not. They are ellipses, and the sun is at the center, or not the center, it's at a focus of an ellipse. And most planets are more or less circular, but I'm going to draw it kind of exaggerated here. All planets move around the sun in elliptical orbits. And we have things like comets that have highly elliptical orbits. They go way out and go around here, but the sun is definitely at one focus of the ellipse. And yeah, so that's another little bit right there. So, okay, that's all we're going to talk about as far as that. Now, okay, when we're going to get into this, so just don't worry too much about what I'm drawing right now. If I were to draw an ellipse right here, and it has a certain formula, which we're going to get into in just a minute, there is a way of finding where those two foci occur. There's something to do with distances of stuff, and it has to do with the fact that any two distances here are constant, the sum of two distances. And it turns out that there's a way of finding what this distance has to be. And so there's a nifty little formula to find this distance right here, and therefore you could find these 2 points. One thing that is kind of important to note is that this is I'm going to call it a horizontally oriented ellipse. Its major axis, this is actually kind of important to know, the major axis is the bigger one. The minor axis is the smaller one. And so it turns out that this one, if it's oriented horizontally, the two foci occur on the major axis, which happens to be here on the horizontal. But if we had another ellipse that was bigger in the vertical direction, and we're going to see plenty of these, so don't worry about this. If we had one that is bigger in the vertical direction, well, the foci occur on, again, the major axis, but in this case, the major axis is the vertical axis. And there's a nifty little formula you could use to find where these points would be. We are not going to worry about that. It's just, as far as I'm concerned, more busy work, and we don't need to worry about that. If you are going to take a standardized test that covers stuff like this, review it real quick and stuff. It's a real simple formula. You could find it. We're not going to waste our time doing that kind of stuff. Oh, actually, there is one more cool application of ellipses that I always thought was really cool. And so I might as well mention right now. There's something called, I think it's called a lithotripter. It could be a lithotripper. I think it's a lithotripter.
Oh, great.
Yeah, don't worry about it. Basically, it's used to break up kidney stones. So if this is somebody's back, and we imagine that their kidneys are right about here, and you have a kidney stone right here, doctors will use a machine called a lithotripter. And what it is a ellipsoid like this. It's, if you imagine you take an ellipse and you rotate it around so that you get this cup. So imagine I've just drawn a cup right there. And right here at one of the foci, we're at one of the foci of this ellipse is a machine that, or speaker, that shoots out very, very high frequency sound waves. And the sound waves all bounce off. It goes in every direction. And the sound waves hit and bounce off the walls of this thing. And you place it in such a way where all of the sound is then focused onto the other focus, where the other thing would be if you had, if you imagine that you continued this ellipse all the way out. But this is how they kind of zero in on where the kidney stone is, and they just use sound waves, and they're all focused. It actually goes through the skin and through the tissues and stuff like that, and the high frequency sound breaks up the kidney stone, and then you don't have to pass a kidney stone, so that's nice, right? So anyway, I think that's also a pretty cool application, but we are more interested in the analytic, the analytic geometry of these guys. And so here we go. Now this is where you got to start paying attention. So finally, we talked last time about circles. Circles, and we're talking about now, this would be a circle centered at 0, 0 right here. And I'm going to go ahead and call this, say this guy has a radius of 1. And so that would be the equation of a circle that is based here at 0. Its center is at 0. It has radius 1, so it goes through here at 1, 1, -1, and -1. So that's a circle of radius 1. It's actually called the unit circle because its radius is 1 unit. Okay, so that's what we talked about last time. So the general form of an ellipse that is centered at the origin is almost exactly like this. The only difference is that we have an a squared and a b squared. And we are going to get into what that does to this here in a second. But first, we're going to look at Desmos and see what that, try to get some intuition on what this is. Okay, so here we go. Desmos. Okay, can you see what we got here?
Yes.
Okay, as you can see, I'm actually plotting two, these are not functions, I am plotting two objects. One of them is the unit circle, x squared plus y squared equals 1. The other one right on top of it is a general ellipse that's centered at the origin. And as you can see, with the A and the B both equal to 1, well, then that second equation is exactly the same as the first equation, because anything divided by 1 is just whatever it is. So now let's see what happens when I let's just say A get bigger. Now, the A is associated there. Now, not by associate, I mean, it's just, it shows up with, it's under the X, right? And so I'm associating it in my mind, there's something with X. The A says to take the X and divide it by something. And so when I make it bigger, I wonder what's going to happen. When I make it bigger, it gets bigger. It actually stretches it out. And now we can see what I'm graphing now is x squared over 2 squared, not x squared over 2, x squared over 2 squared stretches that circle out to, in the x direction, +2 and -2. So let's play with the B now. I'm going to stretch the B up to a 3, and I imagine it's going to do the same thing. Let's just see. Yep, I'm stretching it. It's getting bigger. It's going up bigger. And finally, it gets up to 3 when I'm at B equals 3. This thing is stretched in the vertical direction up to +3 and -3. Another thing to notice that when I went past 2, this thing turned in, this thing turned back into a perfect circle. Well, that kind of makes sense because you have x squared over 4 plus y squared over 4 equals 1. And if I just multiply everybody through by 4, I would have x squared plus y squared equals 4. In other words, I would have x squared plus y squared equals 4. And yeah, that's the circle with radius 2, right? Because 4 is 2 squared. And so, long story short, oops, let's do that. There we go. So long story short, a circle is a special case of an ellipse. And we could write any circle as an ellipse. It just happens to be that both the a squared and the b squared happen to be exactly the same. But when the a squared and the b squared are not exactly the same, then we end up with this oval. We call it an ellipse. Now, check this out. I could make this guy smaller too, right? If I bring him down to 0.5, if I bring b down to 0.5, then it goes through up there at plus and minus 0.5. So, okay, we've played with it on Desmos. Let's figure out why it's doing what it's doing. Okay, so here, like we said before, if this thing that I've written out right now, if the a is equal to 1 and the b is equal to 1, then we just have our regular old unit circle, x squared plus y squared equals 1. But now let's imagine that we don't have that. Let's say that a and b are actually different numbers. And let's do 2 and 3 like we had a minute ago. So let's say we have x squared over 2 squared and y squared over 3 squared. And let's see, why would that do what it did? Well, the first thing we did was play with a, and we saw that it stretched the x values. In other words, the x-intercepts got bigger. And let's see why that would be. How do we find the x-intercepts of this guy right here? What do we need to do?
Y equals to 0.
That y equal to 0, because if you're on the x-axis, that's what we're asking. We're saying, where does this thing go through the x-axis? The only way you could go through the x-axis is if your y value is equal to 0. So let's do that. I'm going to plug in a 0 for y, and I'm going to do this over here because I'd like to keep this picture right here. So I will have x squared over 2 squared plus a big fat 0 over, it doesn't matter, a 0 is going to make that whole thing go away. Now I just have a 1. And so, okay, I have x squared over 2 squared equals 1. So let's multiply both sides. Let's get rid of the denominator. Multiply both sides by 2 squared. I get x squared equals 2 squared. Take the square root of both sides, and I get a plus or minus. Well, the square root of 2 squared is just 2. Okay. So it's kind of nice about writing it in that form as something squared, because then I don't really have to use my brain. I know that if it's doing that, well, to find where it crosses the x-axis, I just say, well, whatever that is, it's going to be up at the positive of it. So it'll be up here at 2. And it'll be down at -2, down here. That's where that thing is going to go through. And we call these points, these 4 points, where it goes through here and here, and where it's going to go through up here and here, we call those the vertices. So those are actually going to be important. I said, don't worry about the foci. The vertices are going to be important. So, okay, we have 2 vertices. Let's find the other vertices. In other words, let's find the y-intercepts. How do we find the y-intercepts of something? Hello?
Sorry, my mom came in.
All right, I saw. Well, I saw that you were looking and talking, and so yeah. How do we find the y-intercepts of this bad boy?
Put x equal to 0.
Set x equal to 0. So I'm going to go 0 squared over 2 squared plus y squared over 3 squared equals 1. Oh, the 0 is gone. How nice. That makes that whole thing disappear. Sweet. Okay, so then y squared over 3 squared equals 1. Oh, that's easy. Y squared equals 3 squared. Take the square root of both sides, and I get y equals plus or minus 3. There we go. And so I go up here, and I'm going to have to draw this pretty ugly, pretty bad. I'm going to go up here to 3, down here to -3, which I can't draw because I put this too low. But you can imagine where it's going to go through down here. And so then this is just really all we've done is we've just taken the unit circle and we've stretched it out in the vertical direction by a factor of 3. We've stretched it out in the horizontal direction by a factor of 2. And so what we end up with is the ellipse that goes through like that. And we're done, basically. If the question was graph this guy, that's how we do it. You'd say, yeah, it's been, the unit circle has been stretched by 2 in the horizontal direction, stretched by 3 in the vertical direction. And if you really wanted to, you could go through and find all those intercepts, or you could just kind of remember, like, that's what this means, right? I could imagine plugging in a 0 and solving like that, but that's exactly what this means right here. So, okay. You got all this? Can I erase this stuff?
1 second.
Okay, give you a second.
Yeah, we're good.
Okay, so problem is it's not the things that we want to graph aren't always given to us in that form. As a matter of fact, sometimes they look something like this. I want to start with an easier one. So let's do that one. 9x squared plus 16y squared equals, I believe it's 144. Yes, 144. Okay. Now, this thing, let's say we wanted to graph it. Well, what I'm thinking is I know what this guy looks like. If I could get this into the form of x squared over something squared plus y squared over something squared equals to 1, and we just saw what that 1 does, right? It really simplifies things because you can just imagine, well, when I plug in a 0 here, the b comes up and it's just, so it goes through the y-axis at plus and minus b, and it goes through the x-axis at plus and minus a. This isn't quite in that form. So what do you want to do to try to put it into this form? There's one big thing that is different. Well, there's a few things that are different. But the thing that really shouts to me is that these are very variable. They're variable. They could be really any two numbers, right? But this, the way that we've written it, this always, always, always has to be 1. So that's usually where I start with these types of things. I just ask myself, is that thing equal to 1? And if it's not, I take care of that. How can I take care of that?
You. Divide
Divide by what?
1. 44.
There you go. All right. And that will turn that into 1. But if I do that, I got to do it to every one of those guys too, right? So we could just put this whole thing over 144, but it's going to be easier because I'm already thinking about, well, it's got to be in this form. It doesn't say to have x plus y over something. I want to try to change that original thing that I had to look more like this. So why don't I go ahead and split up that 144 right here? And so I'm going to do that. Okay, now that's nice because we get a 1 right there. Now 16, I'm moving from right to left for whatever reason. 16 over 144, we should be able to reduce that. 144 I know is 12 times 12. 16 is 4 times 4. Oh, and look at that. 12 is 3 times 4. And so I have a 4 times 4 on the top. Times 3 times 4 times 3 times 4 on the bottom. And so it looks like I could just cancel out a 4 from the top, 4 from the bottom, another 4 from the top, another 4 from the bottom. And I'm left with 2 3s in the denominator. And I could write that either as 9, or I'm kind of looking ahead to say, well, hold up. I want it as something squared. I have 3 times 3. Why don't I just write it as 3 times 3, or 3 squared? That's nice. That's actually really nice. And so now we also could have said, well, what's 144 divided by 16? And we did that and say, well, 16. And then we'd go through and say, oh, it's 9. And you do all this stuff and you find, oh, it's 9. And so you put a 9 on the bottom. And if you did that, right, you'd say, okay, I have this over 9. But then I'm going to stop and go, this is very much like the radius problem last time, right? Like if I had x squared plus y squared equals 16, I wouldn't write that as 16. I would prefer to write it as 4 squared because then I could just see exactly what my radius is. Same thing's going on here. I could leave it as 9, but it will be to my benefit to write it as 3 squared. So I'm going to go ahead and write it as 3 squared. It takes a lot of the guesswork out of these types of problems. Also, now this isn't going to happen with this example, but let's say we had something over something with x squared. And let's say, oh, I don't know, maybe it was 5x squared over 25. And so we reduce that and say, okay, it's x squared over 5. Well, that's not the form that I want. I want to turn that into something squared. And so I would do the same kind of trick I did with my radius in the last lecture. I'm going to say, well, if I need it to be something squared, I could just take the square root of whatever it is and then square it. And that's what I would do right there. In this case, it's not going to work out that way, but this is a very, very nifty trick that we want to keep in our pockets to be able to use as we do these problems. So again, I'm trying to take this original thing and force it into this form right here, where I have x squared over something squared, y squared over something squared equals to 1, and said, well, let's just start by getting this thing equal to 1, and then we'll work out all the other stuff. And so, okay, that's what we're doing. You tell me, what do I need to reduce this guy to? 9 over 144. How do we reduce him?
You get x, or I guess, never mind. You get 1 over 4 squared. So x squared over 4 squared, I think. Over
4 squared? Yeah, I think so, right? Because that's a 3 and a 3. That's a 3 and a 4 and a 3 and a 4. And so the 3s are gone this time. We have 2 4s left over, so 4 squared. Yep. Okay, now we want to graph this guy. Okay. And so this is actually pretty nice because I could see, all right, this has not been shifted. Guess what we're about to do? We're about to shift these guys left and right, up and down. But right now, it hasn't been shifted. This is just like the unit circle, but we're stretching the x we're stretching in the x direction by that much. We're stretching in the y direction by this much. And so where does it go through the x-axis?
We have to set y equals 0, right?
Yeah, that's one way to do it. And what do we get when we do that?
Go through 4 and -4.
Say again?
Would it go through 4 and -4?
Yep. And what about y?
3 and -3.
There you go. That's one of the nice things about writing it in this form. I mean, we could go ahead and define the standard form to be, I don't know, k squared x squared plus k h squared y squared equals m squared. And then we could do other stuff, but it's the reason that we chose to say that the standard form is like this, x squared, y squared, b squared equals 1, is because it makes it real easy to see what the x and the y values have to be. If I want to know what the x is, I basically just cover this up and go, oh yeah, if I were trying to solve this equation, the 4 would come up here. I'd have x squared equals 4 squared, and so it's plus or minus 4. Ditto with y. If I want to know where does it go through y, well, cover that guy up because you're plugging in a 0 for x. The 3 comes up, plus and minus 3. That's where it goes through. And so the major axis is simply the bigger axis, the bigger one of these guys. The major axis is defined to be this length from here to here. It's a length of 8, but that, like that, like that, comes back up like that. And that's my ellipse. I have now graphed, going back to the very beginning, I have now graphed that original thing right there. Okay, so now these don't always come out to be nice, perfect squares, right? Like this case it happened to, and that's cool. But remember the trick, right? If you end up with something like x squared over 5 plus y squared over, let's say 7 equals 1, you'd say, well, I don't quite have it in the form that I'm looking for. And you could just go through and graph it if you wanted, or I mean, go through and solve. You plug in a 0 for say x and you get y squared 7 equals 1. So then you say, okay, y squared equals 7. And so then you take a square root of both sides and you get plus or minus root 7. Or you could say, wait a minute, I'm not quite in that form yet. Why don't I just put this thing into that form? And I'd say, okay, well then we would need this over something squared. We would need this over something squared equals to 1. And so I just take a square root of whatever that is. Happens to be 5, happens to be square root 7. And so I could see if I were to graph that guy right there, I would go, okay. The y goes through at plus and minus root 7. And then the x goes through it plus and minus root 5. And this is really nice about this form is it takes a lot of the guesswork out of this. And we could just really just read it right off of there. And that's why that form exists. That's why people decided this is the one we want for ellipses, because this makes my life way easier like that. Okay, I'm about to throw you a curveball. I'm about to throw you a real big curveball here. Let's do this one. And if this one doesn't come to you right away, don't feel bad. Like, this is tricky because I'm going to show you a trick. Now, once I show you this trick, you'll know what to do from now on for the rest of your life. Let's say we wanted to graph this guy. What do we do? Last time we had 144 and then some other stuff. We said, well, we need to get the right-hand side equal to 1, and then we could go ahead and do that. And luckily, when we did that, it happened to be that the things in the bottom, well, rather, it happened to be that when we divided by 144, it killed those numerators off, and we were just left with stuff in the denominator. But now we don't have that luxury because we already have it equal to 1. Do you have any intuition of what to do with this? It's a trick. And as far as I'm concerned, it's a pretty dirty trick. I think and once you see it, you'll go, oh, ooh, I don't like that. But this is what you do. You say, well, I'm trying to turn 25 into something over something, right? I want to get that in the denominator. So what you do is this. You say, well, here's a trick. I could write that as 1 over 25. Ditto with 16. You could say 16 is the same thing. Multiplying by 16 is the same thing as dividing by 1 over 16 because of that nifty little fact about multiplying by reciprocals, right? Like if I started off by saying, you tell me what this is, you'd say, well, divide by a fraction is the same thing as take your numerator and multiply by the reciprocal. And so you do that, and then you'd say, well, that's 25x squared. And so that's the trick right there, is we just do it in reverse. Instead of saying, well, if you start here, you could turn that into that. We're just saying, well, here's your water. There you go. Okay. We're just using that trick in reverse. We're saying it instead of, because now we are trying to get this thing to get the x by itself. And because that's what we want. That's the form that helps us out. And so we could say, well, we could just do this in reverse, and that actually gets us to where we want to go. We're not quite done because we don't have it in the form of something squared. So what do I do? How do I write 7 as something squared?
7?
Yeah, let's say I had 7 and I wanted to write it as something squared. Think about a radius. What would you do?
The square root of 7?
Square root of 7. Okay, square root of 7. So if I had 1/2 and I wanted to write it as something squared, what would I do?
Square root of 1/2?
Square root of 1/2 is that squared. So if I had 1/25 and I wanted to write it as something squared, what do I do?
Square root of 1/25?
And what is the square root of 1/25? Because I mean, technically we're done. We could just do that, but this one is pretty easy to evaluate. What is the square root of 1/25?
Hold on.
Okay.
Uh, 1/5?
1/5. There we go. And so 1/5 quantity squared. If I could just check that, right? As I go to do that, because I've done a lot of crazy stuff up to this point. I want to double check and say, okay, 1/5 squared means 1/5 times 1/5, which means 1 times 1/5 times 5, which is, yes, 1/25. So yeah, okay, I'm good there. I'm good there. What about 1/16? How do I write that as something squared?
Uh, 1/4 squared?
Say it again, I'm sorry.
1/4 squared?
1/4 quantity squared. There you go. And so now if we wanted to go and graph this bad boy, we could do this. Bad boy. We'd say, okay, x's and y's. So I have my y-axis, I have my x-axis. I'm going to say, okay, x goes through at plus and minus, whatever that number is. And so we have a plus 1/5. And I'm going to exaggerate this a little bit. And minus 1/5. And I'm always going to do this, like, even if they're very close to each other, like, I'm not going to try, I want to exaggerate this so that I can see that the bigger number is 1/4. And so I'm going to say, okay, then this is the major axis right here. It does not need to be drawn to scale, but it's qualitatively accurate. So we could see that, yeah, the up and down way is the bigger way. So then if you wanted to find the foci of this, you could use your nifty little formula that we're not even going to talk about. And we'd see that, well, the bigger one is where the foci occur. So they would occur here and here, but we're not going to worry about that. But anyway, so that's the idea with that. I've looked through your homework and I'm somewhat disappointed that there are none that give you the really, there are a few that you'll have to do this weird trick where you go, wait a minute, I need it in the denominator, but it's in the numerator. And so I'm going to have to go 1/, whatever's in the numerator, blah, 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 to get down here. One thing that they didn't do that shows up in real life, can I erase this stuff?
Yeah.
Okay, so one thing they didn't do that actually shows up is you have something like this. And we want to graph this. And so we go along with the same kind of reasoning. The first thing I do is that equal to 1? No. Well, we better make it equal to 1. So I'm going to go through, divide everybody by 7. That gives me 3x squared over 7 plus 5y squared over 7 equals 1. And then it's the same kind of trick, right? It's like, well, wait a minute. That doesn't reduce. Like when we had, if we had 2/8, we'd say, oh, that's the same as x squared. And everybody just ends up down there because something cancels out. And then we could say, well, that's x squared over 2 squared. Nice, easy. This is not nice. Nothing cancels out here. And we have a problem that we have something in the numerator. And so the trick is still the same trick. We're going to say, well, hold up. If I divide by the reciprocal of 3/7, that's the same as multiply by 3/7. So what I could do is say, well, if I divide this whole thing by 7/3, then yeah, that is the same thing, right? Because doing this in the reverse order, if you were given this, you would say, well, that's the same thing. Oops. That's the same thing as x squared times the reciprocal of that, which is 3/7, which you'd say, oh yeah, we're just put everything over the same divide sign or whatever. And then I could rewrite that as 3x squared over 7. And so this is the reverse of that trick right there. We're saying this isn't the form that I want. I want everybody in the numerator. But I have something in the, but I do have something in the numerator. I want everything in the denominator, but I want something in the numerator. And so what do? Well, I just do this little trick where I take whatever's in the numerator and throw it into the denominator of the denominator. Ugh, it sounds terrible, but I think you see how nifty this little trick is. I don't think this shows up in your homework. And like I said, I'm disappointed that it doesn't. But this is how you would deal with that. If you were to see this, you'd say, okay, well then what does this end up being right here? How do we get rid of that 5?
Um, 7/5.
7/5 in the denominator. Whoever's in the denominator stays in the numerator of the denominator, and then whoever was in the numerator just comes into the denominator of the denominator, because I know the little trick about multiplying fractions. And even as I write this, I kind of take a step and go, wait a second. That divide by a fraction means multiply by the reciprocal. And so this right here would be a 3 on top and a 7 on the bottom. Yes, 3 on top, 7 on the bottom. This divide by a fraction means multiply by the reciprocal. So I would have a 5 on top and a 7 on the bottom. 5 on top, 7 on the bottom. Okay, I'm good to go. One last step. We need to turn these into squares. And so how do I write these as something squared?
The square root.
Square root of whatever it is. So if it's 7/3, I want to say, well, square root 7/3. 7/5, I'll take the square root 7/5. And it looks really bad, but it'll actually help me graph it really easily. I could see, okay, the x is going to be stretched to 7/3. The y is going to be stretched to 7/5. I guess 7/3 is bigger, so I'm going to exaggerate the 7/3 a bit more. So we'll have root 7/3 here, negative root 7/3 here. We'll have positive 7/5 on top, negative 7/5, root 7/5 on the bottom. And we have that nice little ellipse right there. And that should be it. It's pretty much all there is to it. Okay, now shifting these guys. It's exactly like shifting a circle. So just like we talked about last time, the adding and subtracting is still moves the same way. So like with a circle, when I had x minus 3 squared plus, let's say, y plus 2 squared equals whatever the radius is squared. Where did the center end up for that guy?
Uh, 3, -2.
3, -2. In other words, we took a regular old circle, we shifted it to the right 3 and down 2. And so that's why it ended up there. And so the same thing is true here when we have an ellipse. Difference is this is always equal to 1. And then whatever's down here can be variable. So let's say it's 2 squared and 3 squared, and we wanted to graph this guy. The way I do this. Well, actually, what I'm going to do first is show you the way that I don't do this, but what we're actually doing. But this is what we're doing. We're saying, well, wait a second. This is like taking the regular x squared over 2 squared plus y squared over 3 squared equals 1. And I know how to graph that. He looks like this. He goes through at -2 plus 2 in the x, and up here at +3 and -3 in the y. And then we're just taking that picture, and just like we did with the circle, we're moving him right 3 units, and then we're moving him down 2 units. And so we'd say, okay, let's move him right 3 units first. And so we go x minus 3 squared. This is what we're going to do. We're going to graph this guy. We're going to just do one move at a time. We're going to say, okay, if I took this picture and moved it right 3 units, what I like to do is just imagine where each one of these guys goes. If he's at -2 and we move him to the right by 3, then he'll go to -1 to 0 and end up here at -1. I'm sorry, at +1. See the point I was talking about, the left vertex right here? I moved him over 3 units, and so he should end up here at 1. This guy moved over 3 units, so 2, 3, 4, 5. He ends up at 5. And then those guys didn't change at all. They're still up here at +3 and -3. And so, okay, they go through like that. Just like that. Now, finally, I'm going to do my shift down by 2 units. And I can see what that's going to do. He's going to take that 3 that's up here and move it down 1, 2 units up here to +1. And everybody else should shift down. And so let's do it this way. So finally, what I'm graphing is this guy that we wanted to graph, x minus 3 squared over 2 squared plus y plus 2 squared over 3 squared equals 1. And so that was taking this guy and shifting him down 2 units. And so that highest point came down 2 units, and he is now at 1. And then the bottommost point is also still right here. And he is at, we went down from -3, so 2 more, -3, -4, -5. He should be down here at -5. Now, whenever we draw an ellipse, we want to label all the vertices. And so these guys are here and here. And where did they were here at 1 and 5, which means that, well, they haven't moved left or right. Those 2 points were at 1 and 5. So that means they were still up here at 1 and 5, but now they've just been dropped down 2 units. So they're here at, and I'm going to do like this. And this is a hint as to the way that I like to do this. It just got shifted down 2 units. So this horizontal line, the x-axis, basically got shifted down here to -2. And ditto, when I shifted this guy right by 3 units, that major axis, the vertical axis, got shifted over 3 units, and he's right here and goes through at +3, like that. And so that is the ellipse right there. This is not how I go about doing it, though. I'm going to show you the way that I like to do this. And it saves us having to draw it 3 times. And I think once you understand that that's what we're doing, like what I'm about to show you is ultimately all of those steps. We're just going to kind of do it a little bit differently. I think that you'll see that the way that I prefer to do it is a lot easier, and it should make a lot of sense. One thing before we go and I show you that method, we're not done, because this actually goes through right here and right here. And we would need to label those points, right? Because there are 2 extra places where it touches the x-axis. How do I find where something goes through an x-axis?
Set y equal to 0.
Set y equal to 0. And so then you would have, I guess, 2 squared over 3 squared right there. Subtract him off and so on and so forth. You could figure out how to do that. In fact, we'll do it in a second when we go to do this. But so this is what we're doing. We're basically saying any ellipse that you give me, I don't care how it's been stretched or where it's been shifted to, we could think about it as this ellipse that hasn't been shifted in any direction. And then we just go through and shift it to the right or left, and then shift it up or down, and we would have our picture. But we could do that all at once. And that's kind of how I like to do it. So our first step was drawing it, boom, center right here. What you'll notice right here, what I did, I kind of brought that original axis along, and I kept it as a dotted line. So that's going to be my step 1, actually, is to draw a fake axis. Right here. So I'm going to draw a fake axis that I'm going to use with no shifts at all. And I'm going to say, okay. What does that do? So I've drawn a fake axis. And what I'm going to say is we're going to pretend that this is before that thing got shifted. And so if we think about that without the shift, that would just be, well, the y is over 3 squared and the x is over 2 squared. And so I'm just going to pretend that this is my 0. And I'm going to say, okay, the x goes to -2 plus 2. And the y goes up to +3 -3. And down to -3. We'll make this a little bit bigger. Ugh, this looks terrible. Okay, and I'm just labeling, and when you do these, we don't need to worry about, and you can see how this starts to get really ugly here, right? Like if I wanted to label this point as 5, well, that's right next to that. We're just going to put the labels on the points right there. And when you label that far right point, I know that you're talking about that's the x value of that point. So that's how we're going to do it. Okay, so step 1, draw fake axes. Step 2, find the vertices. Step 3, go ahead and draw your ellipse. Okay, so that's what that guy looks like. Terrible looking, terrible. But now what we're going to do is figure out the shifts. And so I'm going to do my x shift first, and I could see that it's a shift right 3 units. So that means, and if we're looking over here, what did we do? We took the ellipse and we pulled that vertical axis over by 3 units, right? So, and right there, I could say, okay, I know I pulled that over 3 units. So that means that my x-axis, so actually, let me make sure I'm writing these down for you. Draw fake axis or fake axes. Dotted fake axes. Find the vertices relative to that fake axis, which is what you do when you're pretending you haven't shifted anything. So that's what we've done right now. 3, do the right left shift and draw real x-axis. I'm sorry, real y-axis. And so, okay, I've shifted this guy right 3 units, which means that I know that the actual y-axis should be over outside of this thing. Should look something like that. Because I'm literally imagining that I've just taken that and pulled him over 3 units, just like this. That's what we're doing. We're pulling him over 3 units, which means that that point that wasn't -2 got pulled out to 1 over there. Four, do your up-down shift and draw real x-axis. Okay, so this is y plus 2, so I know he's a shift down by 2 units. And if I've just taken that thing and pulled it down 2 units, then my x-axis should be up here somewhere. Because 3 is bigger than 2, right? Like it's not going to pull it all the way down. It should still stick up right there. Step 5, label where fake axes hit reals. So in other words, right, I pulled him over. I know that I pulled over 3 units to the right. And so this fake axis hits the actual x-axis at 3. You see how this picture's starting to come together. There's 3 right there. I pulled the fake horizontal axis down by 2, and so I'm going to label right here -2. I'm giving myself some space because I don't want to confuse these guys with those guys. If that starts to happen, use arrows. Arrows are probably going to be your best friend for this type of drawing. And notice I am not labeling these as points like 3, 0 or 3, 1, stuff like that. That again is going to start to be way too much information. If I see that you've put a -2 and you have like a little arrow pointing to that dot, I know that you're talking about the vertical here. When you have a +2 right here, I know that you're talking about how far this way, but we're not done. We're actually going to come back to these guys because we're almost done with this. Now, here's the cool thing. This is the really cool thing. This thing ended up at 5, right? And how did we get that? Well, it's because we were at 2 and we moved over 3 units. In other words, we went +3 to that guy. We took 3 plus 2. So this is part 6. Update your vertices with the shifts. It's terrible. Update the vertices that you originally labeled, your 4 vertices. Update them with the new shifts. So we were at 2, but then we shifted +3. We were at -2, but then we shifted +3. And hey, look at that. 3 plus 2, 3 minus 2. It's as though we said, hey, in the x direction, go to 3, then go +2, then go -2. This is very familiar when we're talking about quadratics, when we're talking about circles. A lot of things have this symmetry where you go to a midpoint or a midline and then go plus an amount, and then you go minus an amount. Same thing right here, right? We ended up down at -5, but why? Well, because you were at -3 and you went down another 2. So in other words, you went -2 minus 3 and -2 plus 3. And you don't need to write that as 1 and 5. I don't care. I actually like it this way, because then as I finally look at this picture that's starting to form, I could say, is this right? Oh, yeah. Look at that. The height, because I know I'm talking about height here for this one, you were at this line -2 and you go +3, -2, -3. That's that point right there. You were here in the center on the vertical one at the point x equals 3, and you went 3 plus 2, and you went 3 minus 2 to get to that point right there. I could see, and I could double check my shifts too. This says to take the entire picture and shift it right 3 units. Yep, that's what that does. It shifts it right 3 units. This says to take the entire picture and shift it down 2 units, and I could see, yep, that horizontal line, you took it and you shifted it down 2 units right there. We end up with the same picture. It's a little bit cleaner right there than how we had it here. Any questions on that that's starting to form right now?
I don't think so.
Okay, cool. So that is how I want these things drawn. We're not done because this thing does go through the x-axis. And so the final step is to label all axis intersections. That does say intersections. You cannot read that. I can't read it. I can't read my own writing. It says label all axis intersections. And I can see by the way this thing is done, right, that we're not going to have, it's not going to intersect the y-axis. So we're lucky there. The only place it does intersect is the x-axis, right here and right here. And one thing I'm willing to bet is that when I go to find these points, it's going to be in the form of 3 plus a distance and 3 minus a distance. Why do I feel that way? Well, because I've been working with parabolas for a long time, and I've been working with circles now for some time. And they all have that kind of property. Like, and oh, and look at that. What are we going to do in order to find the x-intercepts? What do we set equal to 0 to find x-intercepts?
Y equals to 0.
We set y equal to 0. And so I could just imagine what's going to happen, right? We're going to have some number here. That's just going to be some number. We're going to take it over to this side. Then we'll just be left with this. I'm going to bring him up. And then I'm going to take a square root. And then I'm going to have plus or minus the square root of something. And then I'm going to have x minus 3 equals plus or minus the square root of something. And guess what? I'm going to go x equals 3 plus or minus the square root of something. And that's very much what I should be seeing here, right? So the whole time I'm doing this, I'm kind of checking as I go along. Like, wait a minute, hold on. This says 3 minus 2, 3 plus 2. Does that make sense? Well, yeah, because you're going here at 3. These are the x values, and you go to 3 minus 2 plus 2. This says that we're at minus 2, and you go plus 3 minus 3. Yeah, that makes sense. Minus 2, you go plus 3, minus 2, you go minus 3. Okay, that looks good. And right here, the same thing too. It should be equidistant from the number 3. And that's what we're going to see here in a second. So you just told me that to find those 2 points, I take y, set it equal to 0. So let's do that. I get x minus 3 quantity squared over 2 squared equals 0 plus 2 squared is just, plus 0 plus 2 squared is just 2 squared over 3 squared equals 1. Now, I'm going to do this a certain way. Of course, I know what I'm trying to do. I'm trying to solve for x, so I'm trying to get him by himself. I'm working my way out and seeing, okay, well, you got to get rid of this guy next. And so when I do that, I'm going to do it like this. So x minus 3 squared over 2 squared equals 1 minus 2 squared over 3 squared. If I wanted to, I could write that as 4 over 9. Do that. I'm going to leave it, though, as over 3 squared. And so I'm going to rewrite this as 3 squared over 3 squared minus 2 squared over 3 squared. And the way that I'm doing this right now, the way I'm describing how I like to do this, don't need to do, you could just solve this your favorite way. And if you did it right, you'll end up with the same thing that I got. But you'll see why I like to do this way in a second. So that's all over 3 squared on the right-hand side. Let me finish up the left-hand side. Okay. Now the numerator I am going to change now. 3 squared minus 2 squared is the same thing as 9 minus 4. Nine minus 4 is 5, so we have 5 over 3 squared. I did not write it as 5 over 9. I could have, but I chose not to. Now, let me know when you've caught up to here. Okay, so at this point, we are at, and I'm just going to rewrite this right here, just 5 over 3 squared. This is equal to 5 over 3 squared. If you've done this the way that I like to do it, your denominators can always be written as something squared, because that's where it came from, right? Like, you're always going to get it, even if it's something crazy like 7/3, the square root of 7/3 squared. Well, it's still something squared. And so we could keep it in the term something squared. Ditto right here. That's always in the form of something squared. And so I know I'm about to take a square root. So it will behoove me to leave these things as something squared and not multiply everything out. So when I go to multiply both sides by 2 squared, giving me x minus 3 quantity squared equals 2 squared times 5 over 3 squared. When I go to take that square root, this part's going to be super easy for me. As a matter of fact, I could even rewrite that as 2 squared over 3 squared times 5 like that. Again, this isn't necessary. And if you wanted to, you could have said, well, that's the same thing as 5 over 9. And then you multiply both sides by 2 squared, which would be the same thing as multiplying by 4. And so you would have 20 over 9. That's fine. You get to this point and have 20 over 9. That's cool, because we're now going to take a square root of both sides. That's going to give me x minus 3 equals plus or minus the square root of all that stuff. 2 squared over 3 squared times 5. But since I've left it in the form 2 squared over 3 squared, that makes my life that much easier. I could just say that's the same thing as just 2/3 times square root of 5. Or if you like, you could have it as plus or minus 2 root 5 over 3, which is exactly what you'd get if you took the square root of this guy. So I'm making a big point out of, I'm making a mountain out of a mole here, a molehill here. Like, you don't need to do this where you're keeping it that way. It's just, I know I'm about to take a square root, and I don't have to use my brain for this if I just keep the squared parts together, which is always going to happen when you're doing these, because it's always going to be in this form to start off with. So as long as I just keep my denominator as something squared, I could always keep that kind of out front like that, and it'll always work out that way. But at any rate, we're almost done. I'm going to come back up. I'm going to erase some of this right here and continue on with what we got down here. We had x minus 3 is equal to plus or minus 2/3 times the square root of 5, or 2√5/3. That's perfectly fine. Or the square root of 20/9. I don't care. Although, I mean, if you have something like a square root of 9, like, come on, dude, it's 3. Like, let's make it a little bit easier on your teacher, but whatever. So finally, to find the x value, we add 3 to both sides, and we get 3 plus or minus 2√3 times the square root of 5. And we can label these points. And what's really nice is that the way that I've done this, the way that I've set it up, I can see that that makes perfect sense. That this says go to 3, then go plus 2/3 square root of 5, and then go minus 2√3 square root of 5, or 2/3 square root of 5. And so I'm going to label those points right here. 3 plus 2/3 square root of 5. And right here is going to be 3 minus 2/3 square root of 5. And there we go. If there were y-intercepts, we would be solving for them. And here's, I would like to do this. I'm sorry, you may hate me for this. Can I erase this stuff? Do you have this work?
Yeah.
Okay. You may hate me for this, but this is real. Let's just say that you're just plugging and chugging and you're not really taking the bigger picture into play. And you go, oh, I got to find the y, label all axis intersections. So I had better find the y-intercepts as well. The y-intercepts occur where x is equal to 0. And so I get -3 squared over 2 squared plus y plus 2 squared over 3 squared equals 1. And so I say, okay, that's the same thing as y plus 2 quantities squared over 3 squared equals 1 minus, we'll just write it as 3 squared over 2 squared. And so I get 2 squared over 2 squared minus 3 squared over 2 squared is equal to 4 minus 9 over 2 squared, which is -5 over 2 squared. So I say, all right, I'm going to do that trick and say we're going to leave all of those guys out like this. I'm going to bring my 3 squared up top, keep my 2 squared right here. It's a negative, so I'll make it negative, and we have times 5 like that. And then I take the square root, and I'm taking the square root of a negative number. And I go, uh-oh, y plus 2 is equal to the square root plus or minus the square root of something that's negative. And so this is a telltale sign, like if you're doing this and you go, wait a minute, that's an I. I'm gonna have y equals -2 plus or minus I times something. And you go, well, how could that be? Oh, that's because there are no y-intercepts. So my long story short, right? If you end up with an imaginary number, then that's for a reason. In this case, the reason that an imaginary number popped out is because you're imagining that this thing touches the y-axis, but it never touches the y-axis. There's no place where it does. And so you got an imaginary number. So that should be about enough for today. Any questions on this stuff?
No, I don't have any questions.
Say again?
No questions.
Okay. We did not talk about completing the square in order to do this, right? But you've completed the square a lot, and I started off by saying be very careful to use parentheses, because when you factor something out, right, like if you have 3x squared plus 6x plus 2y squared minus 8y equals 0, that we want to be really careful when we go 3 and we factor that out of here, that we're using parentheses when we do our plus and minus the thing squared, that we do that inside the parentheses, because that 3 is absolutely tied up with it. And so when you're going to do this to complete the square and you end up with something like this. And over here, I guess you would have a 2 and a y squared minus 4y. And we'd have a 2y squared minus 4y plus 2 squared minus 2 squared. We're keeping those in the parentheses so that when we go and multiply it back in, we get 3x plus 1 squared minus 3 plus 2, and I didn't do this one. It should be y minus 2 quantity squared, and then the 2 comes back in to give us a 2 times the 2 squared. So that we get 3x plus 1 squared plus 2y minus 2 squared. I'm going to take all of the constants over here. We have a plus 3. 2 times 2 squared is 8. So yeah, because we have a 4 times 2 is 8. And so plus 8, 8, 9, 10, 11. And we have, in this case over here, an 11. Almost done. We need to get that thing equal to 1. So I divide everybody by 11. Then we do our trick because, oh, that didn't cancel out. And actually, I believe every one of your homework problems, it'll actually cancel out and you don't need to do this nifty little trick. But if you wanted to use the nifty little trick, you just say, hey, that 3 comes down here. Hey, that 2 comes down here. And then you go, oh, that's not in the squared form. So you do this nifty little trick. You say, oh, square root, and I square it. Square root, and I square it, and now you're done. But my point is be very, 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 very careful, because now you're going to be factoring numbers out, and you can't just say, oh, add 1 to both sides, or oh, add 2 to both sides, because you're not adding 1, you're adding a 3. In this case, you're adding an 8. And so, yeah, you got to be very careful. So, questions, comments, concerns?
No, I don't think so.
Okay, cool. Oh, we did that one. Okay, I guess I want to sign that one. So, okay, here we go. Homework. First. Quiz redo number 26, I believe it was. Remember my comments from earlier. Then we are doing chapter 10, section 3. Chapter 10, section 3, page 442 through 3. Numbers, we're going to start with that. And we're going to go through 25. Yes. Okay, so no, we'll just do that. 5 through 23. 5 through 23 odd. And they say, so the first part says for each, find vertices, foci, and draw a graph. You could disregard every time it says define foci. We're not going to worry about that. Do read the section about foci and see how you would calculate them, and you could see why we're just going to forget about it. It's just whatever. So disregard foci. The next says for each ellipse, find the center, the vertices, foci, and draw a graph. When the way that I said to do the graph, you will that where your fake axes cross, that is the center. So you don't need to label it or anything like that. So disregard center and foci for that. And for every graph, for every single graph, label all axis intersections. And I would like to see it the way that we did it in class, where you have the fake axes and you shift and stuff like that. label all axes intersections, label all axes intersections, label all axes intersections. Okay, approximate. Then in the next section says approximate the center and the vertices, use a calculator. Please do that at the very end. This is something involving pi. For instance, it says like pi x squared plus pi squared x, blah, 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 blah. So you complete a square, and you have pi that you've pulled out here. And you say, well, I guess it's plus 1/2 of pi minus 1/2 of pi. Like, just pretend that pi is 7 and just go along the way that you'd normally do it, right? There's no reason to use, and in fact, using a calculator too soon will make your life so much harder, because then you're dealing with a bunch of crap in there and it's really a pain. But if you just treat it as a symbol, just pretend pi is some prime number like 7, what would you do? Well, I would divide it by 2 and it would have 7/2 or something like that. And so just do that and you'll get to your answer and you'll have something in terms of pi by how much it's done. And then if you want, you could use a calculator and estimate it and stuff like that. That's cool. I think it's much easier to just do it in terms of pi, and don't let pi scare you. It's just a number and it can't be divided by anything. So just pretend it's 7 and move along, right? So, okay, there's that. Finally, what we didn't talk about, 21 and 23, said it gives you vertices and then tells you to find, what did I say? Number 5 through 23 odd? Yeah. The last thing, it gives you vertices, like for instance, 1 minus 1 or -1 -1. So basically just graph this out, right? -1 -1 is one of them. I'm doing, this is number 24 right now, which is not one that you're assigned, but it gives you 4 points. One is at -1 -1. The other one is at -1 5. And so you go, okay, -1 5. Then it says -3 2. And so we're up here at 2 and -3. And then it says 1 2. And so I could tell that's where it is. Now, this is drawn terribly, but I could see, okay, there's my vertical shift, or I could see, all right, from the center, and this is how I would do this. I would just draw a line and say, well, then from the center, how far has that been stretched? Well, I guess a total of 2 in each direction, right? Because the distance from -1 to 3 is 2, and the distance from here to here is 2. And so that lets me know that my x part is ultimately, this is what I'm looking for. It says to find the equation. And so I know my x part has to be, well, if that half of that total distance is 2, then that has to be over 2 squared. Ditto right here. If we could say, well, the total distance from here to here is 6, that means half of that distance is 3. And so it says go up 3 and down 3. And again, drawing the picture is going to make your life much easier. And so you say, oh, you stretched it up by 3, so that means 3 right here. Finally, you have your shifts and stuff that way. I'm going to say, well, the x got shifted to the right by 1 unit, so that's +1. Got shifted up in the y direction by 2, so that's got to be a -2. And that's how you do those right there. You're basically just taking all of the information that we use to make the graph, but you're just going to do it kind of in your brain in reverse order. So it's all there. It's should be pretty easy. You might want to check a few points at the end, like plug in -1 and 5 into here and make sure that this equation does work. Plug in the point 1, 2. So you plug in a 1 for here and a 2 for there and make sure that, yes, it does work. So that's all I got. This will be due Friday at 8 a.m.